The same exact way that we took 2 points, the initial point and the terminal point of a vector, and created a standard position vector in component form, we can do the exact same thing if our initial and terminal points are defined in 3-dimensional space. We had a formula in the last section for how to do this with 2-dimensional vectors, and we're just going to extend that formula now to our 3-dimensional points and vectors. So if we have an initial point at x1, y1, z1, and a terminal point at x2, y2, z2, we can take this vector, and I'm going to label them just for the sake of naming my vector. Vector PQ in component form we get by subtracting the initial point from the terminal point. So the first component would be x2 minus x1. The second component is y2 minus y1. And the third component is z2 minus z1. So really, the components of a vector are describing the change in each of our coordinates as we move from the initial point to the terminal point. Anytime you see subtraction in a mathematical formula, it usually is representing a change. So also, just like our 2-dimensional vectors, we can define standard position vectors in 3-dimensional space, our standard unit vectors. In 2 dimensions, we had I and j, which represented a single unit along each of our coordinate axes. We're going to do the exact same thing in 3-dimensional space. The only difference is now we need to define all of our standard unit vectors in 3 dimensions. So I is still a 1-unit vector along the x-axis. So it has a component of 1 in the x direction and 0 in the y and z directions. J is still a 1-unit vector in the y direction. And you could probably guess that we're just going to continue on with the alphabet and define our 1-unit vector in the z direction as k. And its components would be 0, 0, 1. So I and j look very similar to how we defined them before. The only difference now is, since these are 3-dimensional vectors, they need a third component. And then we can also use k, which is a standard unit vector in the z direction. With these standard unit vectors, we can, just like we did before, take a vector that's written in component form and very easily write it as a combination of our standard unit vectors. Those components just serve as our coefficients, telling us how far to move in each direction. So we are going to want to express the vector PQ, where P is 1, negative 3, 4, and Q is 3, negative 5, 6, as a linear combination of the standard unit vectors. They're just referring to this format. Linear combination means we're using multiplication by coefficients and addition or subtraction. So what we've been given is the terminal point and the initial point. So we want to create a vector in standard position, and then we want to rewrite it with I, j, and k. So we're going to use both of these concepts here. The component form of vector PQ we get by finding the difference between the terminal coordinates and the initial coordinates. So for our first coordinate, we need to calculate 3 minus 1. For the second component, we use the y coordinates, so negative 5 minus negative 3. And then for the z component, we do 6 minus 4. You have to put those always in the proper order or they'll come out incorrectly. You always want your terminal coordinates first and then your initial coordinates second in those subtractions. So PQ in component form is 2. This is going to turn into a plus, so -2 and +2. And we can also write it as standard unit vectors just by using those components as coefficients. So this also can be written as 2i. This has a negative component, which means we're going to write it as subtraction. We also could write it as plus a -2j, but that's the exact same thing as subtract 2j, and then plus 2k. All of the other algebraic properties of those two-dimensional vectors that we talked about in our last section can be extended and applied to three-dimensional vectors. And what I mean by that is if we're going to add v plus w, we just add corresponding components. So it would be v1 plus w1, v2 plus w2, v3 plus w3. Whatever we do for the first two components, you just follow the same pattern and you do it for your third component. Parallel vectors and collinear points are what we're going to talk about next. So two vectors v and w are parallel if there exists some constant value c such that v is equal to c times w. There is no restrictions on c. We typically will say c can't be 0 just because that would be really boring. If we multiply through by 0, we're going to get 0. But other than that, there's really no restrictions. We can use positive whole numbers, we can use fractions, we can use decimals, we can use negatives. And remember when we talked previously about these scalar multiples, these parallel vectors, they're going to have the exact same or exact opposite direction, but that c value is going to change the magnitude. So if all we do is take a vector and multiply through the components by 3, what we're going to do is create a vector that points in the exact same direction, but is 3 times longer. If c is a positive number, our vectors are going to point in the same direction. And not, sorry about that, not 1, 0. It's bigger than 0. So if c is any positive value, then our vectors will have the same direction. If c is any negative value, that's going to cause our vector to turn around and point in the exact opposite direction. But these vectors are still considered parallel, even if they have opposite directions, because typically where we've used the term parallel before is in describing lines. So if I have a vector that points into quadrant 1, and then I create negative 2v, you see that these fall on the exact same line. So we technically can still call them parallel. Let me just call that negative v. So let's look at a couple of examples. We want to determine if vector v, which is 0, 5, negative 2, and vector w, which is 0, 10, negative 4, are parallel vectors. So we are trying to determine if there is one constant that I can multiply through one of these vectors to get the other one. Sometimes it's really easy to just look and tell, and sometimes it's not. A mathematical approach to this is to create a ratio between the components. and check to see if all of these ratios are the same. That would indicate that there is one particular number that you can use to change one set of components into the other set of components, which would prove that they are parallel. So we're checking to see if these are equal. Now, if we try to do that with our first component, we have 0 over 0. We're just going to ignore that one to start with, because we can multiply 0 by anything and we would still get 0. So we're going to check our other two. So 5 and 10, which is equal to a half. I took the second component here, divided by the second component here. And then check your third components. -2 divided by -4. Again, we get a half. So that's good that they came out to be the same. What this is saying is that W is, no, excuse me, V is 1/2 of W. We could multiply through our W vector by a scalar of 1/2, and that would create our V vector. And what that means is V and W point in the exact same direction. V is just half of the magnitude of W. So yes, they are parallel, because we are able to figure out that scalar. So I've got a second example of this just so you can see one where it doesn't work. If we were to try to set up these ratios between our first components, we want to use vectors S, which is 3, -1, 1, and vector T, which is 6, 2, 2, and see if they're parallel. So for the first components, 3 over 6 is a half. -1 over 2, when we do the second components, that doesn't simplify, that's -1/2. And I can stop right there because I've got two different ratios between two different components. In order to turn 6 into 3, we would have to multiply by a half. But in order to turn 2 into -1, we've got to multiply by a different number, which is -1/2, which tells me that there is not one C value that can turn vector S into vector T. These ratios do not match. You can go ahead and check the third one if you want to. It comes out to be a half, which is good. It matches up with our first component. But if any one of these comes out to be something different, then that means they are not parallel. So our first example, they were parallel, but our second example, they are not. And we're going to use this idea of parallel vectors to define collinear points. Collinear points are points that all fall on the same line. Now, in two-dimensional space, any 2 points, and this is actually true of three-dimensional space as well, any 2 points can always be connected with a straight line. But once you introduce a third point, so I'm going to call this P and Q. Once we introduce a third point, there is a definite yes or no of whether that third point falls on the same line. So if R is here, how I've just drawn, then we could just visually see, yes, they all fall in the same line. But if R was over here, here's my PQ, and I have to change direction to go to R, so that would be a no. So if R was up here, it would be a yes. If R was down here, it would be a no. The idea of parallel vectors can help us with this, because if you have 3 points that you're trying to decide if they are collinear, what we're going to do is we're just going to create some vectors with those points. So there's vector PQ. And here's vector QR. Notice that those vectors are pointing in the exact same direction. They're not necessarily the same length, but if all 3 of those points are on the same line, then those vectors will point in the same direction. If they're not in the same line, then PQ and QR will not be parallel. They point in different directions, completely different directions, not just opposite. So we can take a set of points and create vectors and check to see if those vectors are parallel or not. So right here, we've got points P, Q, and R. They are collinear if vectors, they are collinear points if vector PQ and vector QR are parallel vectors. So we are going to try to decide our 0, -2, 5. I'm going to label that as point P. 3, 4, 4. I'm going to say that's Q. And 2, 2, 1 is my R. Are these collinear points? If we were to graph them, we might be able to just visually tell, but just by looking at those coordinates, it's not very obvious whether or not they fall in a single line. So what we're going to do to check this is we're going to create vector PQ and QR and see if these vectors are parallel. So vector PQ has initial point P, terminal point Q. So you're going to do the Q components, or Q coordinates minus the P coordinates. So in component form, this vector is 3, 6, 9. I did 3 minus 0, 4 minus -2, 4 minus -5. QR has initial point Q, terminal point R, so we're going to do the R coordinates minus the Q coordinates. So 2 minus 3 is -1, 2 minus 4 is -2, and 1 minus 4 is -3. And we want to determine if these two vectors are parallel. So now that we have these vectors in component form, we're going to check the ratios between the corresponding components and see if they all come out to be the same. So 3 over -1 is -3. 6 over -2 is -3. So far, so good. 9 over -3 is -3. Yep, all of the ratios between these components match up. What that means is PQ is -3 times QR. Because we're able to find a constant that relates these two vectors, that means these two vectors are parallel. And if those two vectors are parallel, that means the points that we use to create them must be collinear. So this is a yes. These points are collinear. And then the last thing I want to cover in this section, not really anything new, but just kind of a little bit deeper of an explanation of what exactly component form means. So far, we have defined what component form is. For vector V in three-dimensional space, we'll have 3 components. And one way we can interpret this is that we have a standard position vector, which means it's got initial point at the origin 0, 0, 0, and it's got a terminal point at V1, V2, V3. So geometrically, graphically, that's how we can visualize this vector. Algebraically, though, because this formula for finding component form involves subtraction, another way we can just more generally and algebraically think about these components is that the components are describing the change from the initial point to the terminal point of our vector. And that can be helpful to use, especially if we want to compare this to a vector that's not in standard position. So it doesn't have 0, 0, 0 as the origin. Then V1, V2, V3 describe how we're getting from the initial point to the terminal point. So to kind of drive that concept home a little bit, we've got a vector AB that has component form 3, 0, negative 5. What this means is that to go from initial to terminal point on our vector, for the x-coordinate, you need to add 3. For the y-coordinate, you do nothing because it says the change is 0. And then for the z-coordinate, you need to decrease by 5. So if you start at x, y, z, use these kind of as slopes or rates of change. To get the terminal point, the x has to increase by 3, the y does not change at all, and the z needs to decrease by 5. So this definition is useful if, again, the initial point is not 0, 0. So let's say that point A is 1, 4, negative 2. We can very easily use that idea to figure out what point B where it must be. So we've got initial of A, and it's got x, y, and z coordinates of negative 1, 4, and 2. Now, component form describes how to get to B. So we need to add 3 to the x because the x component of our vector is positive 3. So that puts the x-coordinate of B at 2. The y-coordinate does not change at all because the component is 0. And then the z-coordinate needs to decrease by 5. So 2 minus 5 is negative 3. This puts our terminal point B at 2, 4, negative 3. And we can also use this concept backwards by undoing those changes to get from the terminal to the initial. So we also use components of a vector just in general to describe change.